Thanks very much, Janos and Katerina, for books. Am I muted? Or can you hear me? I'm okay, great. I can see some fingers, thanks. So yeah, it's very nice to be invited and to have a chance to tell you about some of this work. Yeah, I'm joining you from Sydney, which is the relatively recent name for the lands of the Gadigal people of the Eora Nation. So I'd like to acknowledge their custodianship of the lands for tens of thousands of years before now. So this talk is quite combinatorial and sort of it's I think of it as a door opening kind of talk. I'm going to tell you about some relatively recent thoughts about the ways that trees and forests and networks correspond to partitions and covers. And I think of it as a door opening talk because there's not a lot of heavy theorems in here, but there's some really interesting, I think, correspondences that I hope will open the door to some more work. So I'm going to start with a little bit of motivation, which perhaps many of you won't need, but this is the basic layout of the talk. I'm going to start with binary trees and perfect matchings, which is not very new work. It's dates about 30 years back. But then I'll talk about non-binary trees and forests corresponding with partitions and phylogenetic networks and covers. So just by way of motivation, phylogenetics, as I'm sure many of you know, is about trying to represent evolutionary history in a tree or a network. And so this is a beautiful picture from Darwin's notebooks, which makes a lovely tattoo. Whether you include the tree or not, I think is a lovely little scrawl from Darwin. So, you know, we're not going to talk about this today, the process of producing a tree, but just for context, there are lots of different ways to do that, and there's a lot of genetic data available now that drives all of that. And I think the last little motivational point is that you have a problem with sometimes generating the right tree or the right network because it involves searching tree space. So if you're using some sort of MC algorithm or something, you want to walk around tree space and look for something optimal. So you do need a way to encode trees and networks if you're going to do that. So that's about all I'm going to talk about that content. The rest of this talk is going to be very much more combinatorial. So let me tell you what I'm talking about. A tree is, for me, going to be rooted. It's got a root up the top and it's got leaves down the bottom. All of the vertices in a tree, for me, are going to have integer 1, except the root. And everything is going to have out degree either 0 if it's a leaf or more than 1. So I am going to allow more than 2 if every non-leaf vertex has out degree 2. The tree is called binary, otherwise it's non-binary. And I'm labeling the leaves by 1 up to n for some n. So this is the older result that I'm going to use as a launch pad. Diaconis and Holmes, about 35 years ago, proved it's not a difficult result. But it's kind of cute that rooted binary phylogenetic trees correspond with perfect matchings on a set. So if you have n leaves, then your set has 2n minus 2 elements. And a perfect matching is just a partition of that set into pairs. So how it works is you label all the internal vertices of your tree except the root. And there's a nice algorithm to do that due to Peter Erdos and Laszlo Shekele from 10 years earlier. And then so there's a deterministic way to number all those internal vertices. And then each pair of siblings is a set as part of your matching. So if you've got a binary tree, which the result was about, you've got n leaves, there are n minus 2 non-leaf and non-root vertices. So you've got 2n minus 2 labels, and your pairs of siblings provide a perfect matching on that set. So here's an example of how that works. So you've got your tree with the leaves labeled, and you want to label all those internal vertices except for the root. So the first thing you do is you look at the vertices whose children are labeled, and in this case you've got 2 possible pairs. You've got, I'm not sure if you can see my my mouse here, but yes, oh, thumb, excellent. That's technology for you. So you've got 2 and 3 here, or 5 and 6. You choose the one with the lowest label among its children, and you give that the next number in your sequence. So there's 7. And now you do it again. So now you've still got 5, 6, but you've also got 1 and 7 as a pair of labeled children that don't have a parent labeled. So 1 and 7 is the least of these, so it gets the next integer, and so on. So you can label all the internal vertices. And then you pair them off, the pairs of sibling vertices, your perfect matching on the set 1 up to 10. So if you give me a perfect matching on integers 1 up to something, then I can reconstruct the tree quite easily, because the something that my perfect matching is a partition of is 2n minus 2. So I can calculate n and then put n leaves down and then reconstruct the tree in a deterministic way. So that's it's a very simple correspondence between binary trees, rooted binary trees, and perfect matchings. So let's talk about the generalization to non-binary trees and forests, which is, again, a very small step. You know, it's just a little tweak to the idea. If you don't have binary trees, then your sets of siblings are no longer pairs. They're sets of any size, and you will have generally you will have fewer internal vertices than n minus 2. But you get and then of course you get a different correspondence. You no longer have a correspondence with perfect matchings, but you have these 2 perfect. Sorry, not perfect. They're nice, but perhaps not perfect. If you take all rooted phylogenetic trees, then you get a bijection with all partitions of finite sets into non-trivial components, or components of size 2 or greater. And if you relax that constraint, then you've got a correspondence with all rooted phylogenetic forests. So this is particularly nice, I think, just because it's so general. It's just like all partitions of finite sets are in correspondence with rooted phylogenetic forests. So let me give you an example of that. Oh, by the way, this is work with Peter Jarvis from the University of Tasmania. So here's a rooted forest. Forest is just a collection of trees with differently labeled leaves, and it's non-binary. As you can see, there are 2 vertices about degree 3. There's this root up here, and there's this vertex here about degree 3. So it's a non-binary forest, and I've got the leaves labeled. So the algorithm for labeling the internal vertices is the same. I look at sets of vertices that are labeled that have a parent that's unlabeled. So I've got 2, 3, I've got 7, 5, 6, and I've got 4, 9. I pick the smallest and I proceed to label, and I continue. So after that, I've got, I think 4, 9 will be the next. I've now got, I've got 8 and 11 as a pair here, and I've got 7, 5, 6 there. So 7, 5, 6 wins. Now I've got a triple 1, 10, 12. So that's going to win out. So what I'm going to get is everything labeled except the last vertex, and that's going to give me my partition of a finite set. So you'll notice that not only do I have sets of size greater than 2, I've also got singleton sets, and the singletons here, like 13, correspond to the roots of trees. There's always one root that's left unlabeled. So you can also work backwards in the same way. You don't obviously have, with a perfect matching, we had 2n minus 2 elements of the set, and we could get n, but now we have to do a tiny bit more work to calculate what n is. If you give me an arbitrary partition of a finite set, I guess it needs to be ordered have an ordering on the set. Then I can compute n using this little formula. This is the number of distinct integers in pi, the partition. This is the number of sets of size 2 or greater. And so we'll do a little proof of that. It's a short proof. It's a combinatorial proof. You simply count the number of vertices in the forest in 2 different ways. You've either got, well, I guess for that first line, what you need to remember is that every set in your partition of size greater than 1 gives you a parent vertex. So every set of siblings corresponds to a parent. So that means that every set that's of size 2 or greater corresponds to a non-leaf vertex. So the number of all the vertices that you have is n, the number of leaves, plus the number of sets that are of size 2 or greater. And then, of course, there's the other way you can count them is the number of labels on the vertices plus that one unlabeled vertex. So those 2 things are equal, and that gives you that equality in the lemma. So like I said, the theorems are not very difficult, in this talk. That's about, well, there are some that I'm going to leave out, but I guess this sort of argument, the counting argument here, is the sort of thing that it's a lot like a lot of combinatorial proofs. You do have to be a little bit careful, but it's not like you're using perverse sheaves or anything to prove something. So yeah, this is this second lemma is necessary for, suppose you give me your partition of some large set. I compute n, so I lay out the set of leaves. Now I need to reconstruct the forest, and I need to know that there's always a set in that partition that corresponds to a pair of labels with a parent that I can then add a parent to. So that is necessary to prove. I'm going to leave it out for today. So, but here's an example. Here's a little partition of 10. I can compute the number of leaves. This norm sort of pi is 10. The number of sets of size 2 or greater is 4. I've got 1, 3, 6, 2, 5, 4, 7, and 9, 10. So that's 4. So there are 7 leaves. I put them down, and then I look for sets in the partition that correspond to labels that don't have a parent already there. So I've got a couple of options. In fact, I've got 3 options. I've got 1, 3, 6, 2, 5, and 4, 7. I pick the least by the lexicographic order, the least set, which will be 1, 3, 6. Add a new vertex and repeat. And now, of course, I've got another set as a candidate, the set just containing 8. But the least one is going to be 2, 5. So I'm going to rearrange these to make it easier. 2, 5 is the next. And I'll rearrange that again. And now what have I got? I've got 4, 7, or 8. So 4, 7. And now I've got 8 or 9, 10. So 8 is now a root of this in this forest. And now I add 9, 10. And so that's my forest corresponding to this partition. Okay. So what about networks? Okay, if you've got a nice correspondence for forests and non-binary trees and binary trees, what about networks? What can you do? Well, if you remember the whole business, the whole Diaconis Holmes result is built on that labeling algorithm due to Erdos and Shekele. So we're going to build on that, and so this is work with Mike Steele. So for me and for us, the rooted phylogenetic networks are going to be allowed to have a few sort of softened pieces in their definition. So I'm going to have n leaves. They've got out degree 1 and in degree 1 and out degree 0. The other vertices I'm going to allow to have any in degree or out degree greater than or equal to 1. So that means you are going to have sometimes called degenerate vertices of in degree and out degree more than 1, like this one, or equal to 1, like this one. You can play around. So I'm not going to address this in this talk, but you can play around and restrict and reduce restrict the networks to being non-degenerate in this framework as well. You have to do a little bit more work. But that's how net works. And what happens when you try to label the vertices in the same way as you've done for forests and trees? So there's an algorithm, so you might proceed and think, what other conditions or considerations do you need to make? First of all, your sets of siblings are not going to be disjoint, because you're going to have reticulation vertices. Those vertices that have in degree greater than 1 are called reticulations, and they're going to have siblings that are intersecting with each other, two sets of siblings that intersect. So you have to think of a slightly more clever order. So this order is a direct generalization of the other one. So you've got A is less than B if it's a subset of B, or if it's a minimal element is less than the minimal element of, if A without B has a smaller minimal element than B without A. So this is a common natural ordering on sets. So, okay, so you're going to label, and you've got an order, that's fine. Well, you're going to always need to be able to find a set of siblings whose parent is unlabeled. That's going to be necessary, like it was for trees and forests. And you're also going to want each set of labeled siblings to have only one parent. If you have a set of labeled siblings with two parents, the same set with two parents, you don't have a way of ordering those parents, so you can't apply your algorithm. So the first of those conditions is fine, but the second is not fine. So if you have networks with either of these two structures, then you've got a set, for instance, on this right-hand side, you've got this set 3, 4. They're a set of siblings. They have two parents. You have no deterministic way of assigning an order on those vertices to label them, unless you were to think of something else. But just on the basis of the information we're using, we don't have a way to order that. And likewise with these vertices here, this is a small set of one element that has two parents, and I can't label those in different orders. So I'm going to say that a labellable phylogenetic network is one for which that labeling algorithm is well defined. So it's going to require us to not have such vertices in our network. So that essentially is another way of saying it, really, is that the network is labellable if and only if the map of vertices to their sets of children is 1-to-1. So in both of those cases on the previous slide, you had maps from vertices to their sets of children that were not 1-to-1. You had two different vertices that mapped to the same set of children. So you may ask yourself, is it a really great idea to define a new class of networks? And why are we defining classes of networks anyway? So there is a real zoo of phylogenetic network classes, and there's good reason to restrict your attention to a class of networks of some sort or another, because for all these three reasons I've listed here. I mean, if you've got a set of, if you're thinking about trees on n leaves, then you've got a finite set. There's a finite set of trees on n leaves, whether you've got binary or non-binary trees. If you've got networks and you have n leaves, there's an infinite set of networks. So you don't want to be searching an infinite set. Also, if you want to prove things about networks, you very often need to restrain yourself and apply some conditions on the network. But also, just biologically, if you are wanting to infer a network from genetic data on the leaves, then there's only so much you can hope to gather from the historical information. If there's been a lot of reticulation, then a lot of that information will have been lost. So if you're planning to claim that some extremely convoluted historical network is the actual history of your species, and it goes too far with too much reticulation, then there's a difficulty just with the information flow. So there are lots of classes of networks, and you might ask whether the labellable networks are one of those well-known classes. They're not, unless there's a class I don't know about that's not in pictures like this, for instance. But this is a picture from a paper published last year in the Journal of Mathematical Biology. So this is the numbers that are on these edges refer to another table in the paper, which is just the relationships among these classes. But they're inclusions. So the tree-based networks is a large class, and it contains the LGT networks, the orchard networks, the stack-free networks, and so on. And the trees are down here at the bottom. So when we first started thinking about labellable networks, we thought, oh, well, maybe they're just one of these classes. And so that was the obvious thing. Which class are they? So they're not any of these, but it's quite a large class. The orchard networks, which are up here, are quite close to the top, all labellable. And so are the tree sibling ones over here. And I'm not going to define those right now. I will tell you what orchard networks are a little bit later, because I'm going to talk a little bit about classes a little bit later. Yeah, but the labellable ones are sort of above the orchard and tree sibling. And what about, are they maybe all orchard networks, you might say? They're not all, they are not the class of orchard networks, because some of them are not orchard. So the definition of an orchard network, maybe I should give it to you verbally at least now. If you're not familiar with it, don't worry too much, just you'll take my word for it. But orchard networks have cherries or reticulated cherry, and so that's a little structure at the leaves that this network does not have. And orchard networks, they're defining properties that they can be reduced to a trivial network of vertex by cherry and reticulated cherry reductions. So this network is not orchard, but it is labellable. This sub-network is labellable, but it's not tree-based. So the labellable networks are not strictly contained in the tree-based networks. So they're a different class. And some of the tree-based networks, like that little substructure on the right, is perfectly fine in a tree-based network, but it's not labellable. So the labellable networks have a non-trivial intersection with the tree-based networks, which both of them contain the orchard network. So here's a little diagram, which is a Venn diagram to try to show some of these significant classes. I've been trying to make this picture more easy to see without going into some kind of trance. But I don't think I've succeeded. But the large outside ellipses are labellable and tree-based, and then inside their intersection, you've got some of these other classes like tree sibling and orchard. Tree child and normal are both inside the intersection of those. So those are not all of the classes, but they're some of the commonly studied classes. So labellable is quite a large class, and this sort of picture does indicate that many of these classes are all labellable. Orchard and normal and tree child and tree sibling are labellable. Okay, so what about partitions? You don't have partitions anymore because your sets of sibling vertices are not disjoint. So, but you do get covers of a finite set. So this network, which is an example I had up on the screen earlier, if we label it, here we go. Let's have another practice labeling this network. So the first label is 6. So what I'm looking for is vertices whose children are all labeled, that are not labeled themselves. So once I've labeled that 6, this is my next candidate. So that gets a 7. Now I've got this one's got 2, 7, or this one is 4, 7. So that one over there is going to get 8. Now I've got 4, 7 or 6, 8. So 4, 7 is going to win. This one has 5, 9, and 8. and that one has 6, 8, so it should be this one. It's always a bit dangerous if I've done this correctly in my LaTeX earlier on, but yes, I seem to have done this right. So that's a labeling of that network, and then when I put the sets of siblings down, I get this cover. It's a cover of the set 1 up to 11, and you can see it's got singletons. This singleton 3 is because 3 has no siblings. It's a child of a reticulation. And there are sets of size 3. So previously, the forests, I had singletons giving me roots, but now with networks, singletons are going to be children of reticulate vertices. Okay. Some children of reticulate vertices, not all of them. Okay, so I've got a cover. In the cover, you'll see that vertices that are reticulations, so 8, for instance, here is a reticulation, it's got in degree 2. It's a sibling of 6, and it's also a sibling of 5 and 9, and that's 8 is repeated in the cover. So you can find reticulations in the cover by looking for integers that are repeated, and but you'll notice that the leaves are never repeated because they've always got in degree 1. And yes, as I said before, singletons are not roots anymore. Okay, but I've got a correspondence. Well, at least I've told you about one direction from networks to siblings. But if you give me a cover, how do I get the network back? So again, I've got a very similar lemma to the lemma I had for trees, and it's even better because I'm not having to worry about sets being of size 2 or greater. I just take this is the size of the union of all those sets. So it's basically the set of numbers, the size of the set of the number of different numbers I have in my cover. And then the cardinality of C is just the cardinality of the cover as a set. It's a set of sets. How many sets does it have? And again, the proof is the same. It's the number of vertices in the network counted in 2 different ways. So what other properties is necessary for a cover coming from a labellable network? These 2 properties are basically it. First of all, the leaves are not repeated. And secondly, in your cover, if you're going to be able to label the next vertex, you're going to need at least I. So for each I, you're going to need at least I subsets of n plus I minus 1. So the best way to convince yourself this is a requirement is to just do it one at a time. If I equals 1, this is saying that your cover needs at least one subset of n. So I've calculated n using this formula. You give me your cover, arbitrary cover. I calculate n using the formula. So I've got my n dots down for the leaves. I need a subset in the cover from within n. Otherwise, I can't add a new vertex to build up a network, right? And I couldn't have added an extra vertex. So this is a requirement for a network, a cover from a network, but it's also helps me reconstruct the network. So once I've added one label, I need another vertex that has to be a parent of one of these sets of n plus 1. So the second set has to be a subset of n plus 1. So there have to have been 2 subsets of n plus 1, and so on. So if the cover satisfies these 2 conditions, I'm calling it expanding because it's sort of growing, that second condition. And the theorem is that labellable networks are in bijection with covers that satisfy those 2 properties. So there's 2 ways of going. It's a bijection. So if you give me a network and it's labellable, then the cover that I obtain is going to have satisfied these properties. And that's not too hard to prove. And then the slightly harder thing to prove is that if you give me a cover which satisfies these 2 properties, then I can reconstruct a network deterministically that corresponds to that cover. So that's our bijection for labellable phylogenetic networks. So let's do an example. So here's a little cover with 5 sets, cover of the set 1 up to 9. So the double bar of C is 9. There are 5 sets, so there's n equals 5. So I need to know that it's expanding. So I need to check that 1 up to 5 are not repeated. And actually, we can just look at which ones are repeated. I think 6 is the only number repeated here, if I'm right. So 1 up to 5 is not repeated. And the expanding condition, I need to check that there's at least one subset of 5 of 1 up. This square brackets notation means the set 1 up to 5. There's at least one subset of 1 up to 5. There's at least 2 subsets of 1 up to 6, which there are. There's these 2. In fact, there's 3 subsets of 1 up to 6, and so on. There's 5 subsets of 9. That's all. It is in fact expanding. So then I can draw my network. I draw the n leaves. I now have to use my order on the cover. So I'm looking for the sets in the cover that are labeling vertices that are already there. And then I'm going to pick the smallest one of those. So I'm picking 2 here. I add the new label 6. Now I've got 136. Sorry, before this point, I had to choose between 136 and 56. And 136 is smaller, so I add 136. And now I've got, I can't add 4, 8, or 7, 9. So I've really only got 5, 6 available. And I'm adding 8. Now I've got 4, 8. And there I go, 7, 9. That's my network. Okay. So we've got a correspondence between networks and covers. So what can we do with that? Can we encode other properties of networks using covers? And I'll spend the rest of the talk telling you about some of the things that we were able to find. So this is joint again with Mike Steele, but also Daniela Marche, who's in the audience as well online today. Is visiting me at the moment, and it's been a wonderful time. Thank you, Daniela. So our paper's just up on the archive a week or so ago. So let's go through some of these network classes and see if we can describe them in terms of covers. So I'm going to look at, there's a few more that we've talked about in our paper, but I'll just go through some of the sort of larger examples: tree-based networks and embeddings of partitions in covers, tree child networks. I'll talk about fences and crowns. Orchard networks need us to talk about paths and backtracks in the cover, and normal networks. So this, let's talk about tree-based networks first. This is our example that we just reconstructed a moment ago, and I've drawn the cover down here like this just to help me show you about partition embeddings in a minute. So a tree-based network is a network that can be constructed from a tree by drawing additional edges between the tree's edges. So this network here is basically a tree with this extra edge or arc drawn between 8 and 6. If you deleted that and suppressed the vertices 8 and 6, you would have a tree. So that's a tree-based network. So I'm going to redraw it like this. So I'm sorry, I'm just changing it around a little bit to make it planar. Okay, so not all tree-based networks are labellable, as we saw, but we can characterize which networks are tree-based, which labellable ones are tree-based, using this property, this theorem. So remember that the labellable and tree-based networks were both very large classes that have a non-trivial intersection, which contains many of the interesting classes that are in that are commonly looked at. So this theorem characterizes which networks are in that intersection. So your cover, but in terms of the cover, your cover needs to have a fully embedded partition. So it needs to have, there needs to be a partition which embeds in the cover and has the same number of sets as the cover. So, for instance, these are 2 embeddings of partitions into this cover. So the only repeated integer, as we've discussed, is the number 6, which is the only reticulation in this network. So it's repeated. So once you delete one of those 6s, you've got a partition. So each one of these partitions gives you a different support tree for the tree-based network. So the first one is what you would get if you didn't have 5 and 6 being siblings. So if instead you just had 5 on its own, then you would have 1, 3, 6 still, and you would have this support tree. And if you removed, sorry, my 6 has vanished here, but if you removed that 6 from this set in the cover, then you get a different embedding of a partition, or a different partition embedding into your cover. So that gives you a different support tree. So if you have a fully embedded partition in your cover, then you've got a tree-based labellable network. So that allows you to count support trees in a binary tree-based network. We haven't looked at non-binary tree-based networks and counting support trees. I'm sure it can be done, but it's just going to be a little bit more work, obviously. So let's go back to this slightly more complicated example with this cover, and I've highlighted in red the integers that are repeated in this cover. So these are the reticulations. So you can see 6, 7, 8 are repeated. These 3 down here, and 13 is repeated. So it's in 2 sets. So if I'm going to look at embeddings of partitions into this cover, what I have to do is look at the ways to delete the repeats in such a way that I still have an embedding. And I'm going to define a couple of, these are sort of adaptations of other definitions that are in the literature applied to the cover world. So a set of sets in a cover like this, we're calling a crown, because it looks a lot like a crown. So again, this is not our language, this is some other people's language. So if you've got a set of pairs which you can write down in an order where there's 2 of them, and then 1 is repeated from there, and then you get a new one and a new one, and then you cycle back, that's a crown. Alternatively, you could have a pair of pairs, or a set, you could have a sequence of pairs like this that ends with singletons. So 9 and 10 sorry, not singletons, but they're unique. 9 and 10 are uniquely appearing. You might have a sequence like the crown, which just ends with uniquely appearing elements. That's called a fence. And if you think about the different ways you can construct partition embeddings, there's a lot of constraints on them, and it allows you to get this result about the number of support trees in a binary tree-based network. Basically, if you have a crown, if you have anything like this 6, 7, 8 situation here, and you want to count the number of embeddings of a partition in there, you need to pick one of these 6s. And once you pick one of the 6s, if I pick the first 6 here, I have to delete that second 6. And if I delete that second 6, I can't delete the 7 in that set. So I must delete the other 7, and so on. So if you have a crown, once you make a call on one element, everything else follows, and there are only 2 calls you can make. So there are only 2 options for a crown to get an embedded partition. A fence, it depends how long it is. So this fence is the shortest possible fence, this one up here with the 13, these 2 sets here, 9, 13 and 10, 13. R of F is the number of reticulations in your fence, in which case, in this case, it's only 1. There's only 1 in our little fence here. But you could have a lot of reticulations, and so you might have a lot more options with your embeddings. But anyway, you can write down this nice formula. And so if you apply this formula to this example, the number of crowns is 1. So you've got a factor of 2 there, and you've only got 1 fence here, and it's got only 1 reticulation. So it's 2 times 2. There's 4 support trees for this network. This is not exactly the theorem in Pons-Semple-Steele, but it's a very, very similar result that just is equivalent. but it's a different way to derive the same result. Okay, so let's look at tree child networks. A network is tree child if every internal vertex has a tree child. Okay, so it's a nice name because it's intuitive. So this is a characterization in terms of covers. A network or a cover from a network is tree child if every set contains an integer that appears uniquely. So this is also the sort of thing which, if you stare at it long enough, feels obvious. The sets in the cover are labeling children of non-leaf vertices. The ones, the labels that are repeated are reticulations. The labels that are not repeated are tree vertices. So you need to have every set containing a tree vertex. So every set in your cover has to have a uniquely appearing integer. And that characterizes the tree child networks in terms of covers. You just got to look at the cover and say, does every set have a uniquely appearing integer? Yes or no? And that tells you if it's tree child. So this one in particular is not tree child because it has this crown. And if you know about tree child networks, you'll know that crowns are an obstacle to being tree child. But so this is not telling anything new, but it's allowing you to look at the cover on its own and just say, oh, look, there's a set 6, 8. Neither of those appear uniquely, so it's not tree child. Okay, let's look at normal networks. Normal networks are tree child networks without shortcuts. So a shortcut in a network is what you might think it is. I love how some of these names are very intuitive and some of them are completely non-intuitive, but this one is intuitive. A shortcut in a network is an edge for which there's another path going between the source and the target of the edge. So I've got an edge UV and there's some other path going from U to V. So in covers so far, I haven't talked about paths in a network. How do you identify a path in a network in a cover? So we're going to define something called a backtrack to do that. So the labeling order is important too, because what I'm going to do is each set corresponds to a parent, and that parent gets a number in the network. And that number is determined by the set's appearance in the labeling order in the cover. So I'm going to put the sets in the cover in the labeling order, and then they're going to be corresponding to the labels that their parents receive. So as you go through the cover, for each I, the ith set is the minimal remaining set in this n plus I minus 1. So we'll see an example in a second. And a backtrack for x, if you give me a vertex x, a label x, a backtrack is a sequence of sets which basically walks up the network. Okay, so I'm going to start with a set that contains the number, and then I'm going to go next to the label of that set and a set containing that label. So maybe an example will make that clearer. So this is that example we had before. You can see the 6, 8, 6, 7, 7, 8, that's the crown. The 9, 13, 10, 13, that's the little fence that was there. This is the cover in labeling order. I'm sort of drawing like this way is a shorthand for drawing a set of sets with these sort of mids, these partition bars, but they're really sets of sets. So this subscript at the back of each set is increasing from n plus 1. And I'm going to add a row on for the root onto the very last set. And so this is like, if in this case, n equals 5. So 6 is the label of the parent of 1. So that's the labeling order of the sets. So then 2 gets a parent labeled 7 and so on. So this is a deterministic thing. You give me the cover and I can lay them out in order, and they've got a label on them. And then I can define this backtrack, say, for instance, for 3. 3 has label 8. That means the parent of the vertex 3 is 8. So I'm looking for a set containing 8. There's a couple of choices, and I've picked one. So this is a backtrack. There are several backtracks for each element, often. So here's one, and then the label of that is 12, and then I look for a set containing 12. There's only one here, and the parent of that is 13. So I look for a set containing 13. There are 2, but I've picked one, and I keep going like that. So I can move back through the network from 3 all the way up. Get a backtrack. So that allows me to define a shortcut in terms of the cover. A shortcut is simply a backtrack of X that includes a set containing X. So if I have a set containing X, and if I start with X and I have a backtrack, I'm looking up at the parents and a path up through it. And if I hit a set that contains X in it, then that's an edge going all the way back down to X. So that's a shortcut. So I can identify shortcuts in the cover by looking at backtracks in the cover. And so I can now identify normal networks. I have to look for each X, for each label, that the cover has no backtracks of X that contain X. So I have to do a bit of work to check for normality, but I have to do that anyway with normality. I'm going to be looking for shortcuts. So it's requires a little bit of work. So I don't think this is necessarily shortening the algorithmic check, but it's restating it in terms of the cover. Okay, I'm nearly finished. I'm going to do very briefly orchard networks. Orchard networks are those that can be reduced to trivial networks by cherry reductions, like this one on the left. This is a cherry. I'm reducing it by replacing this cherry just with a vertex labeled U, or this reticulated cherry, this structure, which gets reduced in this fashion. We delete that reticulate arc there. And in terms of covers, there's a simple operation on the sets. So you can translate that cover, that reduction to covers, and describe an algorithmic test, which again, I'm not going to go into. So this is a summary picture. I'm not going to talk about any more classes. There are a few more classes in this picture. This is our attempt to draw a map of network class space. There's a couple here that I haven't mentioned. So this is the labellable tree-based networks in the middle. Tree-based networks, this is the condition you must satisfy. Labellable networks, this is the condition you must satisfy. Orchard networks, cherry reducible. Tree child networks, satisfy that. These are tree sibling networks, haven't talked about those. Spinal networks, everyone's favorite network that nobody knows about yet, but spinal networks are another class we defined just by tweaking the definition of expanding cover, just for fun. They're in there, and this is normal networks and trees. So it's a different map based on cover properties. So just, I'm going to skip ahead in conclusion. None of the tricks we've pulled in this little story are very, I don't think they're not very dramatic tricks. I think the original Diaconis Holmes idea about binary trees and perfect matchings is resting on a very natural vertex labeling algorithm. So you go from a vertex labeling algorithm to perfect matchings for binary trees. You relax the binariness and you relax the treeness, and you get I was going to say perfect again. You get a correspondence between forests and all partitions of finite sets. And that opens the door. I haven't mentioned this at all today, but that opens the door to a lot of algebraic things, because one of the leads that Diaconis and Holmes left was you can use Brauer diagrams maybe to move around tree space. There's a lot of semigroup questions there that we've just started looking at. And finally, if you relax the tree assumptions to networks, then you get covers. And we're able to interpret a surprising amount, I think, of network properties in the context of covers. So I'm kind of excited to see if we can push that door open a bit further and see what the whether we're in a dusty backyard shack or a mansion that's got interesting things to find in it, and we don't quite know yet, but we'll find out. So thank you very much for listening. I know I've run right up to the time limit, but thanks for being there, and thanks to my collaborators Peter, Mike, and Daniela. And I'll end there. Thank you.